Okay. Predicting precipitates. What we're going to work on is, well, trying to predict whether precipitate's going to form or not. They do this a lot. In the environment, there's a lot of heavy metals, chromium, mercury, a lot of things that just are not good for you at very, very trace levels. But a nice thing about them is that they can form, several of them can form precipitates at very low levels. So you can use these types of analyses to figure out what's in the environment. Metallurgy, they're doing this all the time. I bet you San Antonio River Authority is really worried about precipitates. We have an aquifer that has a lot of metals in it. And if these metals start precipitating out, oh yeah, you're going to have a lot of pissed homeowners. But the city, yeah, I'm sure the city's concerned about that, but they're more concerned about their own pipes, right? That stuff starts clogging up. Look at billions of dollars to replace. It's not going to work. It's not going to happen. So they got to be monitoring all these simultaneous equilibria at the same time. And they're adding chemicals to there to keep precipitate from going out. Or they're removing compounds. And now what they're worried about is a lot more complex, I think, than what we're doing because it's multiple reactions at the same time. But the fundamentals are the same. So this is useful stuff. Now, to make our life simpler, though, I strongly suggest reminding yourself a couple solubility rules. One of them is what cations in water can never, ever be a part of a precipitate. Now, the cations were, Genevieve, the positive or the negative ions? The cations were the positive ones. Mariella, do you remember what cations never form precipitate, ever? You put these cations with something that's 100% soluble. They never form precipitate. It was group 1. So you have sodium, potassium, lithium, right? Okay. Anions, negatively charged. I can only really think of one, and there's really only one that's applicable. Anyone know which one I'm thinking of? Not fluoride. And the reason why I know not fluoride, because if you look at a KSP table, there's fluorides in there that are parts of precipitate, so that's not it. Starts with an N. Nitrate. You'll never form precipitates with these guys. So if you see a nitrate or if you see a group 1 metal, they're never going to form precipitate. Let's take a look at this and see if we can get at what I'm trying to show you. Okay, I'm going to pick two solutions. I'm going to pick sodium chloride and silver nitrate. Now we're going to mix those two solutions. Lewis? Is there a possible precipitate? Now remember, you don't look at group 1 metals, you don't look at nitrates. What's the only possibility? Okay, yeah, Ag and the Cl, right? Silver chloride, AgCl, is probably the only possibility here. Does everybody agree? All right, so let's say yes. And let's say AgCl, they're going to dump the two together. Then they're going to make a little movie and see if little AgCl starts forming at the bottom. There they go. Ag is the silver and chloride anions are green. And they just start precipitating out. Okay. Let's try sodium chloride. Oh no, let's try this one and that one. Silver nitrate and potassium hydroxide. Jessica Vaughn, is there a possible precipitate? Ooh, she got it. The Ag and the OH, right? The cation's always first. Silver hydroxide. Where is it? Here it is. So let's see if little silver ions and hydroxide start precipitating out. There they go. The silver spheres and the OH, oxygen's red, hydrogen is a little light blue. They start precipitating out. And there's one combination left here. I haven't done, what? This one and that one. Yeah, okay. Sodium chloride and potassium hydroxide. Matteo, is there a possible precipitate there you could guess?
Oh, well, no. No, you can't, because you can't.
All right. The only thing you could really mess with is the OH negative and the Cl negative, but you can't have two negatives, so no. So that means these ions should just be floating around, and you shouldn't get any precipitate. See, there's the OHs, chlorides, sodiums, and potassiums. Yeah, nothing's precipitating. Okay, so I think you got the idea. Here's the homework question. They're going to give us two solutions. And they're also going to give us the concentrations usually. And the question is, hey, are you going to get a precipitate? So here's the game plan. That's what we just did. You figure out what the possible reaction is. What's the possible precipitate? And then you write the little reaction for it. Now, we had to know how to write Ka reaction. We had to know how to write Kb reaction. What type of reaction, Javier, is this? A K what reaction? What do we call this? What's the KSP? Remember that. Okay? If the solid is on the reactant side, and all of its ions are on the product side. So you write the KSP reaction for the precipitate that you think might form. And then you go and you write a QC expression. We've done QC before. It's called the reaction quotient. Victoria, do you remember when we did this? We wrote reaction quotient expressions before. It was to answer a particular question. And the question wasn't, are you going to form a precipitate? No. The question is, are you at equilibrium? That's it. Are you at equilibrium? You see, you plug in all the concentrations of products, divided by the concentration of all their reactants, raised to their stoichiometric coefficients, right? You get that QC number, and you compare it to the equilibrium constant. They had to tell you what it was. And the only time it's at equilibrium was when, what? Equal, right? That's not this question at all. This question is, are you going to get a precipitate? They don't care about equilibrium. Okay? Are you going to get a precipitate? So let's see how this is going to work. We're going to calculate our QC expression, and it's products over reactants. In this case, for a KSP reaction, Pablo, how would you write it? Products over reactants. So in brackets, you're going to have, yeah, and little b goes where? Yeah, as the power raised to the little c. Then everybody, it's all over 1. So you plug in these concentrations, raise them to their stoichiometric coefficients, right? Raise them to their powers. You get a number for QC. Right? You get a number for it. Then there's 3 possibilities. Either it's going to be exactly the same as the KSP, or it's going to be smaller or bigger. Now, where do you get these KSP numbers, Destiny? Yeah. Tables. So you just got to look them up for whatever the solid is we're interested in. If QC is equal to KSP, you do the math, Mallory, the number you looked up in the table. Would you expect a precipitate? Yeah. Oh, it's at equilibrium, definitely. That is a good point. It's at equilibrium. This one, I could honestly go either way on it. But I know the book has a technical answer. And I can understand their technical answer. It's at equilibrium. You're right. So that means that, dang, you're not going to see it. It's not going to be a big lump on the bottom. But if you I don't know, you have to get a dang microscope or something. And there's going to be some little crystal in there somewhere. I'm sure you can't see it because you're right at the threshold. And yeah, technically the answer is yes, because there's some little microcrystal in there. There has to be. Okay. You do the math, you get your reaction quotient, Eddie, and this time you compare it to KSP, and it's too small. Now, Eddie, these equilibrium constants, they're all what over what? Products over reactants. So if QC is too small, I have too much or too little product. Too little, because QC is too small, right? Because product is on top. I have too small product. Look and see what your product is. It's right here. So it's going to shift. Now, whose principle are we messing with? Le Chatelier. So are we going to? Should we expect it to precipitate then? No. Le Chatelier. Yeah, I can't see it yet. Okay. QC is bigger than KSP. Now we have too what product? Too much product. So now it's going to shift to the reactant. So should we expect to precipitate? Yeah. So there's two possibilities, two cases where you should expect a precipitate. When you nail the KSP or when QC is too big. Okay, here's our first one. Amanda, we've got a solution of lead 2 and a solution of chloride. We're supposed to say, hey, do we expect to precipitate? The first thing is to write a plausible KSP reaction. What KSP reaction could we write? Is there one? PbCl2. In fact, I like writing the ions first, because then it's easier to write the solid. What are the ions? They're Pb and you're right. It will be 2Cl, but it's Cl minus. Over here, write the solid and put their charges in there, because it's so much easier to figure out what the formula is. Because remember, you just move the charges as to the subscripts. The 2 over there and the 1 over there. And now you're right. You got to have the 2 chlorides over there. It's not balanced. And don't forget to write a what subscript? Solid. S. There it is. Okay. So my reaction quotient, Vanessa, QC expression would just be what? Concentration of lead 2. And don't forget to do what to the chloride? Square it. Okay, so that means we have lead, which is 0.035. And we've got chloride, which is 0.15, but don't forget to square it. And we get, someone borrowed my calculator. What do you get? Thank you, sir. Pretty much 7.9 times 10 negative 4. Okay, now we need a KSP. For lead chloride. So let's hand this out to Jeff right here. We need a KSP for our precipitate there. What is it? Okay. So we got to compare KSP and QC. They're definitely not equal, Sylvia. How does QC compare to KSP? QC is what? QC is 10 to the negative 4 and 10 to the negative 5. Bigger, right? QC is too big. So that means I have too what product? Too much. So it's going to shift the reactant. It's going to shift to that solid. Right? So the answer is, yeah, you bet. Yes. Expect a PPT. Okay. So it'd be nice if the homework stayed that way, but there's no job security in easy problems. No, there isn't. Anybody and everybody can do it. Okay. This is more real life. You have 45 mils of 0.0015 molar barium chloride, and you dump it in 75 mils of 0.0025 molar potassium chloride. The question is, do you expect a precipitate? So, Nick, we do the exact same thing. First, we figure out, hey, what's a possible KSP reaction? What could it be?
No.
How about just the barium chloride itself? Right? Look at that. You have barium chloride just sitting there itself. You see what I'm trying to confuse you here, but look at this. You have BaCl2 that's just there. Why couldn't that be a precipitate? There's two guides to why you don't write a KSP reaction for barium chloride. One is, look at this thing. What does big M mean? Molarity. It's a solution. It's not a precipitate. The other thing you could do is take a look at your KSP chart and you look for barium chloride. There's no KSP for it. So BaCl2 is not a possibility. Now BAF fits our rules. KCl doesn't. The BA and F do, right? Okay, so let's write BA and F, and we can figure out all this stuff. What ions, Jessica, Rojas, do we put over here? BA plus 2. Now, how did she know that the BA was plus 2? She's exactly right. Good, exactly. You can either look at the periodic table or recognize that little 2 right there. Okay, so we have to balance it. Oh, we're not even right here. Yeah, then 2 of those, and don't forget the F. Okay, we're getting close. Adrian, how do we write our QC expression?
QC is BA plus 2, and then
In bracket.
and then half squared.
Yeah, over 1. Okay, let's start with the concentration of the barium. Is the concentration of the barium, let's change this here, let's pick the color here. Shelby, where's my barium coming from? It's coming from this thing. Is it 0.0015? It's 1 to 1, right? If you have barium chloride, you break it up, and you get 1 barium. You see what I'm driving at? And you have this, if you just had 45 mils of barium chloride solution, that's it. Just that solution. It's this nice, pure 45 mils of 0.0015 molar barium chloride. The concentration of barium would be 0.0015 because it's a 1 to 1 ratio. The concentration of chloride, that's kind of a trick question. You get 2 chlorides for every barium chloride. So the concentration of chloride would be 0.003, double it. But we're not interested in that. We're interested in barium. The concentration of barium, if it was pure, would be 0.015. The problem is we screwed it up. We dumped in what? We changed the volume. The D word, we diluted it. It's not 0.0015. It's something less. So we have to actually calculate it. We're going to have to what is concentration? It's what over what? It's moles over liters. Okay. Now we can handle the moles part. How do you get the moles of the barium? Oh, you can do what Adrian's talking about. This is how we handle it. N equals moles over liters, and you treat it as an equation. Big M is, what do we say, 0.0015 equals moles, and the liters is going to be 0.045. That's what we took. The other way, I kind of like the other way better, and my way is, well, my way, or what, it doesn't really matter. 0.01 big M is moles over liters. If I just take it times the number of liters, but you get the same answer. Okay. What do you get? 6.75. 6.75, Adrian, times 10 to the negative 5? Okay. That's what we should get for the moles. The liters. Yeah, it'd be more descriptive if we wrote total liters. But, just realize it's the final concentration of barium. So it needs to be the total liters. There you go. Has to be in liters. Add 0.045 liters plus 0.75 liters. Okay, so in the end, our barium is going to be that 6.75 times 10 to the negative 5 moles all over the total volume. We'll add that up, by the way. About 0.12 liters. So I got about 5.625 times 10 to the negative 4, big M. Okay. So divide the moles by the total volume. Now we have to do the exact same thing for the fluoride. Again, remember it's moles over liters. Find the moles, find the total volume, divide the two. What's that? Oh, once we get the fluoride, yeah, you're right. But we have to get it first. Now our fluoride was up here. .75 mils of 0.0025 molar. So we'll have 0.075 liters times
0.875.
Right. And the total liters, have to add them up again. Well, that'd just be 0.12 liters again. All right, it's the same total volume. Same thing, 1.56. I'm just going to write a bunch of digits. Who cares? So 0.00 or 1.56 times 10 to the negative 3, same thing. So there's our fluoride. Now we have to substitute that stuff into our QC. Is 5.625 times 10 to the negative 4. And our fluoride, but we've got to square it. I got 1.37 times 10 to the negative 9. So that's how I got my QC. Let's do this guy. Okay. Yeah, now we need the KSP. Got to compare KSP and QC. We need KSP for our precipitate. Thank you, sir. 1.0 times 10 to the negative 6 is my KSP. QC is 10 to the negative 9. So 10 to the negative 9 is smaller than 10 to the negative 6. So I don't have enough product. Yeah, I don't have enough product. It's got to shift that way. No precipitate. No precipitate. Okay. So in these questions, identify what the possible precipitate is, right? It's KSP reaction. Calculate the concentrations of the ions involved. Compare it to KSP and predict whether the precipitate will show up or not. So try this one. You have 65 mils of 0.01 molar lead-2 nitrate. And they're going to dump that into 40 mils of 0.035 molar potassium chloride. You're supposed to determine whether a precipitate is expected to form or not. So identify a plausible precipitate, write its KSP reaction, and calculate a QC. Good. Just write a little F there. Exactly right. If you're not sure if your KSP reaction is right, you can always check the table. There has to be a KSP for it. Otherwise, it doesn't exist as a precipitate. Technically, that guy should be a negative. Yeah. Should have a little S there and a +2 in there. Good. I think everybody pretty much agrees on the reaction. Jessica, what did you get for the lead 2 concentration? For the lead 2 concentration, did anybody else get 6.19 to 10 negative 6? Okay, a bunch did. That's got to be right. Okay. Chloride. Jessica, what'd you get for chloride?
1.26 times 10 to the negative 4.
Let's see if you got that one right. How about the chloride? Did you get 1.26 times 10 to the negative 4?
We're like still on the word.
Chloride. 0.013. Alexa got 0.013. All right. Several folks got 0.013. I bet you that's it.
I did.
Okay. Several folks got that. Make sure those. What'd you get for your QC? 1.09? Did you get this for your QC then? 1.09 to negative 6? You get that for QC? Pretty close?
I got
1.05.
Oh, okay. Yeah. All right. So. Lead chloride. 1.6 times 10 to the negative 5. So my QC is too small. All right? Not enough product. So if you got this one, go on to the next one. Oh, you can't see the next one? Here you go. And now you can do the next one. You have to write the QC expression. Products over reactants. So here it is. Yeah. Oh, you got it. The 2 doesn't go there. The 2 always goes as the next one.
Oh.
Stoichiometric coefficient. No. Yeah, like that. Concentration of chloride squared. You should technically have a +2 on the lead. Let's see, what are the charges? Let's see. S is going to have a -2, and Fe is going to have a +2. But yeah, with ionic compounds, it's the simplest ratio. Good. For this one, your reaction should be Fe +2 and S -2. All right, good. It's always, for ionic compounds, it's the simplest ratio. Not for molecules, but for ionic compounds, yeah. Probably, you have to go look. In the computer. I can't do it in my head. So we're about out of time. Come by if you have some questions.